Okay, we're picking up in the second half of Notes 3D, picking up with example 6, where we're going to talk about half-life. And, this is something that you've heard from your science classes from day one, all the way back into middle school when you started having science separately. And you would hear about half-life, like the carbon dating that they would do on dinosaur bones and that sort of thing. And they would take the carbon and they would calculate, they knew what the half-life was supposed to be of carbon. And so they would look at what was left and they would project backwards to figure out when did this start decaying. And this gives us something to work with. Now true, scientists have to figure out what is the half-life of a given element. Now, in this particular problem in front of us, we're looking at polonium-210 has a half-life of 140 days. Now, I'll say this, your half-life time period, T, is going to be time in whatever units that you're dealing with here. Polonium-210, it's in days. Carbon-14, it's more like years. There are some things that have a half-life in terms of seconds. So it just depends on the units that you happen to be using for, the half-life of that particular element. Now, one thing that is worth pointing out is that in this formula where I see R, I'm going to have to come off to the side and calculate what R is based on the half-life and then take it back to the equation. Now, M sub O is the original mass, and E, there's our friend E from natural logs, and then time is going to be in whatever time, in this case it's days. And so first of all, let's go off to the side and calculate R. If R is natural log of 2 over the half-life in this thing is 140 days. So when I calculate that, and I'm going to get a decimal to 4 places. I'm getting a decimal that is 0.00495. And after that, it's like a 1 and a 0. So 495 is probably a good place to round it. And I would definitely keep like 4 or 5 decimal places on this thing because by the time you start raising stuff exponentially, you're going to go through decimal places pretty quickly. And the more decimal places we add here at R, the less we have of rounding errors that we've talked about at other times. All right, so we're supposed to find a function that models this thing. So we're going to say M of T. M sub O, the initial mass, was 300 grams. And then there's E. And then there's negative 0.00495. And then there's T, because we don't know what the time is yet. They haven't asked us about it yet. So that's, basically all we have to do is plug in the time, and we can come up with the mass of whatever polonium-210 is after that many days. So let's try it, what happens after a year. So we are going to say M of 365 equals 300 times E to the negative 0.00495, and that is 365 days. Again, it's in the same units. Your half-life was in 140 days, so we need 365 days just to keep the units consistent. Now, this you can punch into the calculator, but I'm going to make this recommendation. When you punch it in, you do it something like this. Because when you raise that E to an exponent, it starts you off with a parentheses. Just go ahead and put the negative decimal and the 365 multiplied inside the parentheses, close off the parentheses, and you should get an answer. And that answer is about 49.256 to be exact. since everybody seems to be in whole numbers for the most part, we'll leave it that way. Okay. All right. Now, I will go ahead and warn you, as I'm thinking about it, I don't think this happened in the notes, but along the way in the worksheet, at one point, I'm going to ask you to reverse engineer what was the half-life. And you're going to have to figure out, well, what was R? And if R equals natural log of 2 over H, then I should be able to solve for H and tell what the half-life was. So you will be asked to do that. I don't think I have a direct example of that in the notes. All right, so what if the sample, how long to decay to 200 milligrams? Well, so 200 is where you're going, 300 is where you started. That is your R value, and we don't know what T is yet. So probably the first thing we'll want to do is to get the 300 away from the E. Now I am going to leave this as 2/3 because I don't really want to round anything unless I absolutely have to. Now, I probably am going to do this because we're at the stage to where we can rewrite this as a logarithm now. We're going to say log base E, and my exponent is going way over there. And the 2/3 is going here. Now, log base E, you might as well say natural log of 2/3. And so we're going to take the natural log of that and then divide by the negative decimal. All right, so the natural log of 2/3 is going to give us negative 0.4 and some change. And then when we divide both sides by that negative 0.00495, we're actually going to get 81.9. We'll just call it 82. And how long? This was in days, so it would take 82 days for it to reach that level. Now, we're going to move on to Newton's law of cooling. This is, if you'll forgive the pun, this is really cool. It is, because right now we're talking about things like cups of coffee. When you get into the worksheet, you're going to get into things like, pulling a turkey out of the oven. And I think we even get into things like dead bodies cooling. That's what's going on with CSI, is that they're talking about the rate at which a body temperature, internal core temperature, cools at a certain rate after a body dies. And so they can use that. They understand the curve there, so they can use that to predict when the body actually stopped breathing. And so I think you'll be using it. And the thing is that each substance that is cooling, whether it is coffee or turkey or a dead body, has its own constant of cooling. It cools at its own rate. And for the most part, that rate should be consistent. From if I'm dealing with coffee, it should be roughly the same thing from one coffee to the next. Of course, you add cream and sugar, that changes things, but you get the idea. So first of all, they've given us information about a cup of coffee that it was 200 degrees Fahrenheit when they put it on the counter. Of course, 212 is boiling, so that's really, really hot coffee. After 10 minutes, the coffee is 150. So we have to figure out what is the constant so that we can create a model equation for how fast that coffee cools down. Now, one of the things that's involved, there are two things that you need to pay attention to here. T sub S is the surrounding temperature. well, in this case, the surrounding temperature is 70 degrees. And then D sub O is the difference originally. Well, if the coffee was 200 and the room was 70, the difference is 130 degrees. So that's the D sub O. That's what's going to go there. So we're going to write out, if the surrounding temp was 70 and the difference was 130, 200 minus 70, and times E times negative K. Now, the thing is that they're giving us a specific here. After 10 minutes, the coffee was 150. So I've got enough plugged in there that I should be able to solve for K. Now, K is up there at the exponent, which means that we're going to do some logarithms somewhere along the way to get K by itself. But first, we're going to use some pretty standard rules of algebra. I'm going to subtract 70 from both sides. I'm going to divide both sides by 130, which I'm going to reduce that down to 8/13 equals e to the negative 10k. And I'm going to bring that over here because we're going to rewrite that as a logarithm. Log base e, exponent goes over there, 8/13 goes there. Well, log base e, that's really natural log. So what we're going to do is we're going to figure out the natural log of this fraction and then divide it by 10, and we'll be there. All right, so the natural log of 8/13 is going to be negative 0.4855. And then when I divide by negative 10, I get 0.4855 equals K. So I figured out what the K constant is for coffee. Do not be surprised if some of these are in 4 and 5 decibels. All right. Again, when you're raising E to a power, you can lose decimal places real quickly. That number will get big and fast. And if you round too close, if you round it to 2 decimal places instead of 5, you're going to discover your answer drifting from what everyone else is getting. So, all right, now we're going to take this over here and we're going to find out, so what happens in 15 minutes? All right, so we need T of 15 equals 70 plus 130 times e to the and it's negative kt, so it's still going to be negative 0.4855, and the t is now 15 minutes. Now, honestly, this you can just about punch into a calculator. I think what I would do is I would punch the e to the exponent first, and then multiply by 130, and then add 70. And the thing to remember is that when you're putting, this e up arrow, parenthesis, negative, yada, 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 times 15 and then close the parenthesis. And you'll get like 0.48 for that. And when you multiply it by 130, you should get 62 something for that. And then you add 70, and you're going to get 132.75 something, about 132.8. So find the temperature of the coffee at 15 minutes. It is about 133 degrees Fahrenheit. Okay. And that is the last of the notes.